Okay, good morning, students. Let us start with the most important topic for this module number 3 or for all this syllabus. That is second order RLC step response. So we have seen so far the modeling of RLC circuit, and then we have seen how to find out the transfer function. Then we have seen what are the different pole positions for different damping conditions. So there are four systems we have talked about. The first system was undamped, zeta is equal to 0. We had found that the performance is like a oscillatory movement. Then we had increased the value of R in damping. We increased the damping zeta in between 0 to 1. So for your simulation, you can keep the damping as 0 0.1, 0 0.15, 0 0.2, zero point 0.3. So don't go beyond 0 0.3 because lesser is the damping, better oscillation you will be able to see during your simulation of experiment number 5. So this experiment number 5, this theory of module 3, they all go hand in hand. So there are mainly two parts in this module 3. One is the RL and RC circuit step response, impulse response. So that partially we have done. A lot more numerical have to be solved. We will do it after this second order RLC circuit. And second part is the second order RLC circuit. So yesterday we have done some simulation. Some more simulation is to be done, but today we are not going to do it. The plan is today we will complete the theory and different numerical of second order RLC circuit. So I will start exactly where I left in yesterday's lab session. So all the lab videos, all the lab theory, everything is uploaded. So after we complete today's session, this PDF that I had shown you, that will be uploaded. So almost 28 students are there. So this is the topic for today, that is derivation and time domain specification. So the derivation will be asked in the exam. It is little big, but it is not difficult because it is the same as finding transfer function first and then finding the step response, and not very big derivation is there, but yes, to understand the real essence of second order RLC response, we have to understand the derivation. And I requested you to keep calculator, pen, paper with you as long as this third module is going on. So today also we will be requiring calculator, pen and paper. So please get it. I give you 2 minutes time till I launch this PDF of mine. Please get calculator, pen and paper, because some numerical we have to do. We have to calculate theta in radians and all these things. That is not possible by simple calculation. So you need calculator for that. So I am stopping my presentation here. I'll be launching my PDF and you get a calculator as soon as possible. So I think my screen is visible to you. So let us start this proof. So it's a 15-page document, and this document will be uploaded to you. And there are 6 to 8 numericals. Every numerical is very important. They are repetitive, but they are very important. So I would ask you to prepare all these numericals, solve it on your own once you get this document today. So this lecture video and this numerical PDF, 15-page PDF, this all about second order system. Okay, first page is about first order system response, how to find it. This we have seen yesterday. Second page is about RLC, this proof, we have done it yesterday. So for RLC system, we found that the transfer function is 1 by LC S square plus R by L S plus 1 by LC. Then this Cs by Rs, this is a generalized form of second order transfer function. So we had compared these two, then we found omega and natural frequency is 1 by root LC. That is the first parameter. So there are two parameters in case of second order RLC system. First parameter is omega n in radian. The formula is 1 by root LC. Second parameter is zeta. So whatever R by L is there, so this transfer function we have got from V output by V input of RLC circuit. Output is taken across capacitor. Input is given in the series circuit of R, L and C. So if you just compare this 2 zeta omega n with R by L, so these two transfer function you have to compare. First, by comparing omega n square with 1 by LC, we have found omega n is 1 by root LC. Unit of omega n is radian per second. Next, you have to compare R by L with 2 zeta omega n. So already you know what is the value of omega n. It is 1 by root LC. So zeta is equal to, so 2 zeta by root LC is equal to R by L. So if you shift it, you are going to get zeta is equal to R by 2 root under of C by L. Now there are four cases possible. First case, keep R is equal to 0. You are going to get zeta is equal to 0. That is the most unstable. I repeat, that is the most unstable response when we keep zeta is equal to 0. What we get is there are two poles, complex conjugate poles which are on j omega axis, and we find a sustained oscillation or sinusoidal waveform. Then we keep R value as, suppose, let's say 0.3. C is equal to L is equal to 1, so zeta is equal to 0.15. What we get is response is sinusoidal, but it is decreasing sinusoidal, it is converging sinusoidal. So what are the pole position? In that case, pole position shifts towards the left hand side of j omega axis. It's a complex conjugate pole, both are imaginary poles. So in that case, the response is decreasing kind of sinusoidal. We have seen all those waveforms yesterday. Today we had planned to do some MATLAB based thing, but no, that we will do next day. Today we'll solve numericals on this, design numericals, which are generally asked for 10 marks in exam. So that is R by 2 root under of C by L, but system is still stable because it's a sinusoidal, but sinusoidal is diminishing kind of sinusoidal. Okay, so this is instability reduces a bit. So for zeta is equal to 0, instability is maximum. Zeta is equal to 0.15, instability reduces a bit. So as zeta increases, stability increases, and as zeta increases, the instability or instability, it reduces. Then what we do is R is equal to 2, we keep C is equal to L is equal to 1. So in that case, zeta is equal to 1. This is called as a critical damping situation. So in case of critical damping, there is no oscillation found in the system output. For step input, we get kind of almost step kind of output. So for zeta is equal to 1, it is called as critical damping, and we find output is rising very fast. In the last case, we had seen R value we can keep very big. So 6, 7, 8, something you keep. C is equal to L is equal to 1, you keep. So we find zeta is equal to 3, zeta is equal to 4, which is called as over damping. So we'll find that the output will reach to the input, that is 1, but quite a lot of time late. So as you are increasing the zeta, the response of the system is becoming stable, and as you are increasing the zeta, stability of the system is increasing. So these are the things we had seen yesterday, and we had seen something like this. So there are two more factors. One was omega d. So whenever it is underdamped condition, omega d is equal to omega into root under of 1 minus zeta square. So what is omega d? It is called as damped frequency. So if omega n is equal to suppose 5 radian per second, omega d always will be less than 5 radian per second. So what is omega d called? It is called as damped frequency or damped natural frequency. Formula is root under of 1 minus zeta square. So omega d exists as long as zeta is less than 1. Whenever zeta is equal to 1, at that time in this formula you will find omega d is equal to 0. That means at critical damping, omega d is equal to 0. And at over damping, omega d is a imaginary quantity. So at zeta greater than 1, omega d does not exist. Now position of the second order poles. So this was yesterday's part. So what we found was this is the standard transfer function, and in this standard transfer function, denominator equation is called as characteristic equation. This equal to 0 if we do. Roots we find as minus zeta omega n plus minus omega n root under of zeta square minus 1. So here this root under of we take minus outside, so this becomes plus minus j omega n root under of 1 minus zeta square. So first case zeta is equal to 0. If zeta is equal to 0, if we just put it, we are going to find that S12, that is the roots of the equations or the poles of the system should be plus minus j omega n. That means, sorry, this was the second case. First I have to start with this. So this case. So if we are plotting zeta is equal to 0, we find plus minus j omega n. the poles are on the j omega axis. In that case, we find steady transfer function. That is, we are finding, actually this is a sinusoidal waveform, but this is a cosine waveform and inverted. Okay, it is starting from 0, then it is showing some oscillation with a function of omega n. So that is the zeta is equal to 0. Then what we do is, in the same equation, this one we find zeta as 0.15, that is in between 0 to 1. There is the underdamped condition. Zeta less than 1, zeta is 0 to 1. Zeta cannot be negative and zeta does not have any unit. If you're doing that, you're finding both this real part and imaginary part, both are existing. So in that case, you are going to get pole positions like this. In that case, we'll be finding that the response of the system is like this. There's an underdamped response, CT, very big response, very big equation of response. So this is the main thing we are supposed to derive. This is the CT. There's the step response. So input is step 1 and output is oscillating, and after that it is getting stable at 1. So this response we are going to see today. We are going to find what are the different parameters. Then for zeta is equal to 1, you are finding this critical damping. In that case, there are two real poles, both are at minus omega n. Okay, so both are at minus omega n because we have put zeta is equal to 1. And then zeta higher value we have put, we are finding that there are two poles, real poles, but they are at different positions on the minus sigma axis. That is negative real axis of S-plane. There are two different poles, and the response will be like this, but response is slower. So critical damping and over damping both are not having any oscillation in them. Undamped and underdamped both are having oscillation in them. So these are the two things you have to remember. That is critical damping and over damping. There is no oscillation, there is no frequency component, sine or cos. But in undamped or underdamped, there is sine or cosine components present. So whenever the system is becoming critically damped or overdamped means here the system is very highly stable, gain of the system is less. So as damping increases, system gain reduces. And we told you that damping and gain, they are inversely proportional, and damping and stability, they are directly proportional. So as damping is increasing, the system stability is increasing. So we stopped here last day. Today we are going to see with the proof. So already 4 pages are down. It's a 15-page document. So in 2-3 pages, this proof will be there. So again, we are starting with CS by RS, omega n square, S square, 2 zeta omega n, omega n square. And then you are finding these roots. So yesterday only we had found these roots. So after you are finding the roots, minus a plus minus jb. So don't worry about these very big factors. Okay, this omega n root under of 1 minus zeta square, this is omega d. And this is zeta omega n. This is actually called, I think is that, this is called something. Okay, we will see what is this thing called, zeta into omega n. It will come in our proof. This thing will come. What is zeta omega n called? Okay, so in this case, if you're finding the standard transfer function of second order system, now here one thing I would like to tell you that this is, though we are doing it for RLC, but the same proof will be applicable for MBK system as well. Because in the MBK system, the omega n will be something different, zeta will be something different formula, but omega n and zeta, all these things will be there. So I'm doing it for RLC system, no. I'm doing it for MBK system, no. I'm doing it for actually second order generalized transfer function. So any second order system, let it be RLC, let it be MBK, let it be hydraulic, pneumatic, let it be any system. Okay. In that case, the second order transfer function and its step response proof will be same. Only the formula of zeta and omega n will change like this. So poles are at S1, 2. We have seen this thing previously. So CS by RS was omega n square plus S square plus 2 zeta omega n plus omega n square. If you're just showing it after finding the roots of it. So here you are finding the root is minus zeta omega n minus j omega n root under of 1 minus zeta square. Here you are finding the root is S is equal to minus zeta omega n plus j omega n root under of 1 minus zeta square. So this multiplication equal to 0 is the characteristic equation. Now we are supposed to do the CT, or CT is nothing but the step response of the given system, given RLC system. So the same thing, CS by RS is this transfer function, which we called as TS. So now take RS in the right side. So I have taken the RS in the right side. So CS is equal to omega n square by S. So see that this S has come here. So omega n square into these two poles, omega n square into these two poles, but 1 by S has come. What is 1 by S? 1 by S is nothing but the RS, because RT is equal to UT, RS is equal to 1 by S. So RS here actually I'm calling as input. Don't confuse it with the ramp, because some book RS, R is taken as the ramp. We can take it also, but in this case RS is the input, and input is step because we are trying to find the RLC system step response. So that's why this S has come. The question is asked suddenly why this S has come, because RS is 1 by S. So CS by RS I have taken to the right side, RS into omega n square, and RS I have substituted as 1 by S. Now you find there are three terms. So here the step is shown actually. This step is actually, it had to come up and this step had to come down. So that is not a problem. Another substitution we have done, that is omega n root under of 1 minus omega zeta square. We have substituted with omega d. So you can see here the same equation is written here. So this CS and this CS, they are actually same. But what we have done is S plus zeta omega n plus J, and this whole part is called as omega d. What is omega d? It is the damped natural frequency. And always the value of omega d is less than omega n. I told you if omega n is equal to 5 radian per second, omega d will be less than 5 radian per second. And as zeta is increasing, when zeta is equal to 1, the value of omega d is equal to 0. So the relationship between omega d and omega n is as zeta increases, that means as system goes towards some more and more stable condition, in that case the damped natural frequency will reduce, and whenever zeta is equal to 1, at that time omega d is equal to 0, system will not be having any oscillation in that case. So the same thing I have done. So remember one substitution, that is omega d is equal to omega n root under of 1 minus zeta square. So now CS is equal to, there are three terms, denominator S plus zeta omega n plus j omega d, S plus zeta omega n minus j omega d. So if you're mixing these two, if you're multiplying these two, it comes as S plus zeta omega n square plus omega d square. Now no need to do this multiplication, because actually we are supposed to do the partial fraction of this. But this is another CS equation that I wanted to show, and that's what I have multiplied it and shown it. But actually next proof is in the next page. So what we are finding is we are doing the partial fraction. And after partial fraction, you are finding numerator is S plus zeta omega n, denominator is this, omega d is equal to omega n into root under 1 minus zeta square. So they look very big, but they're actually not difficult, because numerator there was S. So on that, this is 1 by S minus, this is the positive root, this is also another root. So these are the two roots, and S plus zeta omega and all those things has come. And if you are taking the inverse Laplace transform, so you won't have to show the inverse Laplace transform. Directly after this line, you can come here, and finally what you are going to get is this thing. So Ct is equal to 1 minus e raised to minus zeta omega n t. So all the parameters we should know. What is that? So 1 minus e raised to minus zeta omega n t. So it is like e raised to minus at. And zeta is the value of underdamped condition we have seen. So zeta can be 0, zeta can be in between 0 to 1, zeta can be 1, zeta can be greater than 1, all those things we have seen. What is the value of omega n? It is equal to 1 by root LC. So we should know everything in the terms of L and C and R. So zeta is equal to R by 2 root under of C by L. Omega n is equal to 1 by root LC. Here also zeta, that is R by 2 root under of L by C. So if I give you a circuit, RLC circuit, you should be able to write this equation directly. Okay, and again here is zeta, that is R by 2 root under of C by L. Omega d is 1 by omega n into root under of 1 minus zeta square. Omega n is equal to 1 by root LC, zeta you know, and sine omega dt. So everything we have to write in the terms of L and R and C. So I'll give you just a RLC circuit and I'll ask you to write the CT equation. You should be able to write. So for that, first what you have to calculate, omega n 1 by root LC. Zeta you have to calculate, that is R by 2 root under of C by L, and just keep on substituting. So what we are finding is, if we are substituting the value cos alpha is equal to zeta, here sin alpha is root under of 1 minus zeta square. So here we are finding this 1 minus zeta square we will substitute as sin alpha. This zeta we will substitute as cos alpha. So in that case it is becoming sin alpha cos omega dt, cos alpha sin omega dt. So that is actually sin A plus B formula. So finally CT equation. What is CT? CT is called as, now listen carefully, CT is called as step response of RLC second order system. That is given by 1 minus e raised to minus zeta omega n t. We can calculate what is zeta, we can calculate what is omega n into sin omega dt plus alpha. Okay, what is alpha? Alpha is nothing but the phase of the waveform. Whatever CT you are finding, what is the step response in time domain you are finding. So we know what is the CS by RS. We substituted RS in the right side. Then we had found the partial fraction. After that, whatever CS we have found, this is step response in Laplace domain. Now we have to take the inverse Laplace. Then we have to do some manipulations and all these things. And directly we are coming here. That is Ct is equal to 1 minus e raised to minus zeta omega and t root under of 1 minus zeta square sine omega dt plus alpha. So this thing, if you remember, this is enough. Omega d is nothing but damped frequency and alpha is nothing but the phase. And what is alpha? Alpha is equal to tan inverse root under of 1 minus zeta square by zeta. So only one thing unknown here, sorry, two things unknown here. One is omega d, omega and root under of 1 minus zeta square. Second one is alpha, tan inverse root under of 1 minus zeta square by zeta. Now the biggest caution I am telling you, so this is one formula. This is another formula, Ct is equal to 1 minus this omega dt plus alpha, or the standard formula is this. If you are substituting omega d, if you are substituting alpha, in that case you are getting the big formula. So if you really want to create an impression, you have to write this formula. Okay, or if you want a shorter formula, you want to like you write like this. Both the things are correct. If you are writing the top formula, in that case you have to write about omega dt and alpha separately. So write this formula and say omega d is equal to omega and root under of 1 minus zeta square. Write alpha and say that alpha is equal to tan inverse root under of 1 minus zeta square by zeta. That is not a problem. So here you are finding that it is, so this root under of 1 minus zeta square, it's just a constant factor. So don't worry about that. Who decides the shape of the waveform? Now I'm coming to the main mudda. Who is going to decide the shape of the waveform and what is the shape of the waveform? So this one is a DC. It is not going to change the shape. It is going to change the shifting. So top shifting. So whatever is the output, it will be shifted upward. Okay. So this is actually an exponential waveform, e raised to minus at, decreasing kind of exponential, and this is a sinusoidal component. So this delay and all those things, you don't worry about that. Only you have to see what is the frequency of that. So frequency is omega d or 2 pi into f. Okay, so you can find what is f from here. So there is a frequency here, sinusoidal frequency. That means there is a sinusoidal waveform, and there is a exponential, decreasing exponential. So decreasing exponential like this and sinusoidal. So if you just multiply these two, if you impose a decreasing exponential on sinusoidal, what you are going to get is it is a decreasing kind of a sinusoid that you are going to get. So that much you have to understand. Don't get scared looking at this very big formula. So root under of 1 minus zeta square, it's a constant. Okay, suppose if zeta is equal to 0.8, so zeta square is equal to 0.64. So 1 minus 0.64 is equal to 0.36. Root under of 0.36 is 0.6, and 1 by 0.6 is around 1.6. So this is a constant. Don't worry about that. E raised to minus zeta omega and t. Let's say omega n is equal to 10 radian per second and zeta is equal to 0.1. Okay, so omega n into zeta is equal to 0.1 into 10, that is 1. Okay, so e raised to minus t, in that case we are going to get. Here also omega t, if omega n is equal to 10, you can calculate how much is omega d because zeta is equal to 0.1. So in that case zeta will be almost very small, okay, and calculate this. So don't get very much tensed looking at this formula. Here it is nothing but e raised to minus at sine bt, that kind of a thing. What you have to understand is there is a sinusoidal waveform with a frequency of omega d, and it is not a sinusoidal of constant amplitude. It is not a sinusoidal of constant amplitude because it's multiplied with a decreasing kind of a exponential. So this is an amplitude of decreasing kind of exponential, and this is the sinusoidal. If you multiply that, you are going to get a reducing kind of sinusoid. And reducing kind of sinusoid means system is going to be stable because waveform is reducing. Whenever the waveform is increasing, if instead of e raised to minus zeta omega and t, if I say it is e raised to plus zeta omega and t, then it is getting multiplied with sinusoid, and then it is going to be an increasing kind of a sinusoid. In that case, it is going to be a unstable response. Okay, so if we find that poles are there in the right hand side of S plane, in that case, this will be e raised to plus zeta omega and t multiplied by sine the same quantity. In that case, it will be a sinusoidal but multiplied with an increasing sinusoid. That means as the time goes by, this sinusoid is going to diverge, okay, and it is going to explode, or value is going to increase exponentially. But for poles left side of j omega axis, this is e raised to minus zeta omega and t. This is a decreasing kind of exponential. When it is multiplied with sinusoidal, it is going to produce a converging kind of waveform. So now we are supposed to see different parameters of this waveform. So how this waveform looks like, I will show in the next page. But before that, there are some two notes. So this is the output response of second order underdamped system with step input. Underdamped means zeta is in between 0 to 1. So as long as zeta is in between 0 to 1, this is going to be the response, or actually this is the standard response. You substitute different values of zeta and you are going to get what is going to be the CT of this equation. So that question will be asked in the exam, that first find what is the standard CT equation and substitute different value of zeta and get those four responses. So substitute zeta is equal to 0. So if you're substituting zeta is equal to 0, you'll be finding that this is going to give you sine. So zeta is equal to 0. That means denominator is 1. Numerator is also e raised to minus 0, 1. So you are going to get this is sine omega dt. Okay, if you're substituting zeta is equal to 0, this is sine omega dt. So 1 minus sine omega dt. Likewise, you are going to get. That means it's a sinusoidal response. Likewise, if you substitute zeta is equal to 1, at that time you will be finding that there is no oscillation in that, because zeta is equal to 1 if you are substituting. This part is going to be 45 and zeta is equal to 1. So in that case, this part is going to be 0 because this is omega d. So sine 0 means this part goes. So likewise, you will be finding all the responses. So we will see shortly how those responses look like. So this is actually the second order system. Not only RLC, it can be RLC, it can be MBK, it can be any system. Okay, so this is going to be the second order system time domain response for step input. That is very important because this 1 has come because there was a S, 1 by S. Okay, S at the denominator, that's why there was 1 by S. From that, this 1 is coming. Okay, and what is the second order RLC system or MBK system or second order hydraulic, pneumatic, any system, any second order system will be having this kind of response. And any second order system will be having two design parameter. One is omega n, another one is zeta. So omega n is given by 1 by root LC, zeta is given by r by 2 root under of c by l. So that is for RLC. For other systems, that equations will change. Now see, so exactly this kind of response we are going to get when we do in the MATLAB. So maybe tomorrow, day after tomorrow, within this week only we will do it, but today's time is transfer function. So what all things we can find here? So response is starting from 0. Okay, so you have given a step input. First you have to understand that. So what input we have given to RLC circuit? We have given a step input, and this is the response. So input and output is very important. What input we are giving, where we are giving the input, what output we are getting, and across which parameter or across which component we are getting the output. So what is the input? Input is unit given to a second order RLC system, and from where we are getting the output, output is taken across the capacitor, and this is the input. So input is rising very fast like this 1, and output is actually going to rise like this. Okay, and it is going to oscillate across this final value of 1. So this is the oscillation. So this is the transient period. From here the output started building up until here. Okay, it is almost touching to 1. Okay, this is 1 is steady state, and after this point the steady state value of 1 is continued like this. So initial part from here up to this point, so this time is called as a settling time, that is given by TS. And steady state starts. So what is the definition of steady state will be different in this case. So there will be a 2% settling time, there will be a 5% settling time. What are they? We will check shortly. Okay, you know at this point that the response started building up from here at t is equal to 0. What happens at t is equal to 0? We give the step input to the RLC circuit and output across capacitor. So output across capacitor is voltage build up in the capacitor. So that voltage actually increases very fast. After this time, delay time, which is called as TD, the voltage across capacitor is 50% of its final value. The final value is 1. Okay, and time after TD time, TD seconds, the output is 0.5. After TR seconds, the output is same as the input. But output does not stop here. Output crosses the input and goes above and comes below, goes above, comes below. So it is kind of oscillation. So there is some cosmos kind of thing going on inside the system. Energy and system, they oppose each other and all those things. And after a certain time, which is called as 2% settling time or TS, let's say settling time, the output of the system is same as the input. So from here to here, from starting point to this TS, this period is called as transient. Very important thing you have to know. Whenever system is any system, so we are also a system. I told you that whenever you join the college for first 1 or 2 months, tum log idhar udhar jaate the, kuch bhi karte the, you are not stable. And after that 1 month, you knew the department, you knew the college, everything. So you have started producing a stable response. But for initial first 1 month or so, it was very unstable for you. So that is the step. Okay, so whenever the step input is given to the system, initially it shows some kind of undulations and a lot of oscillations and all, and after that it gets stabilized. Okay, so this period is called as transient, and in this transient period we do not find steady state error. Don't go on finding steady state error when the system is unstable, when the output is varying. Okay, you have to find steady state error when the system has got into steady state. That means after the time TS. And here if you are finding output is 1, input is also 1. So at steady state, you find what is the difference between system input and system output. So here system input is 1, system output is 1, so steady state error is equal to 0. So here something is written 2% error band, 5% error band. I will discuss it some other time. So CT is equal to this, and this is the response. What all things we are supposed to check here? TD, in how much time the system goes to 50% of its final output. Final output is 1, 50% of that is 0.5. Okay. TR, rise time, how much time it goes to 100% of its final output for the first time. So here also the output is 1, here also the output is 1, so there is crossover point everywhere. But these are not TR. TR is for the first time when the capacitor charges to 100% of the input. So that is called as TR. This is called as peak time because here the waveform is going to the peak. And percentage MP. Percentage MP means if this voltage is 1.4 and input is 1, then percentage MP is 40%. Okay, if this peak voltage is suppose 1.37 and input is 1, in that case percentage MP is 37% likewise. And the time when the waveform gets completely stable, it enters the steady state zone, this thing is called as TS. So from starting to this point, this thing is called as TS. Here we are finding something like 2% TS, 5% TS. We will explain this thing later on. So now we are supposed to do this proof. So this proofs I am not going to do here in the lecture, but all these proofs are given in the book of M. Gopal, starting from page number 241. So prepare all those proofs. 3-4 line proof is there. You have to find the differentiation of this CT and all those things, and you have to find what is the different values of other things. Now you get your pen and paper because we are going to do the numerical shortly. Delay time, that is 50%. It is given by 1 plus 0.7 zeta by omega n. This is the formula. Rise time TR, pi minus theta. Now this is the point every student is doing a mistake. Pi is given in radian. Be very careful whenever you are calculating pi, it should be calculated in radian. Degree का कोई स्थान नहीं है यहाँ पे. Okay, in this numerical, nothing is calculated in degree. So whenever you are going to do the second order RLC system numerical, first thing is you have to keep your calculator in radian mode. Pi you have to substitute as 3.14. Pi by 2 you have to substitute as 3.14 by 2. 2 pi you have to substitute as 6.28. Likewise, this theta is also calculated in radian. What is the formula for theta? Tan inverse root under of 1 minus zeta square by zeta. Here, just find out. Okay, so this is what is called as theta. So here students are making mistake and losing directly 10 marks because you are calculating omega n, you are calculating delay time, you are calculating tan inverse, all this thing in radian. But whenever you are doing the second order system response, there is nothing in degree, everything is in radian. So pi and theta are in radian, omega d is radian per second, pi is 3.14, theta is in radian, theta is root under of 1 minus zeta square divided by zeta. The rise time is time taken by the system to reach from 0% to 100% of its final value. Then there is coming peak time, that is pi by omega d, pi is 3.14. Then there is coming settling time. Okay, so there is something called as 2% settling time and there is something called as 5% settling time. So what is 2% settling time, which is more accurate? 2% settling time, TS value is more, 5% settling time, TS value is less. Actually, we are trying to find out when this response is entering. So final value of the response is 1. So this thing generally students don't understand in the first shot. Try to understand. So this system is going here. What is the value I said? The value is 1.4 and actual input is 1. So how much is the error? Error is 1 minus 1.4, that is 0.4. Okay, so how much is the error? 40%. So this first you have to understand. Okay, at this point, let's say at this point the response value is 1.4 and input I am giving as 1. Input is always 1 because this is unit step. So 1 minus 1.4, because how do we find the error at any instant? Error is nothing but input minus output. So at this instant, how much is the error? And error is not constant because output is varying. So as output is varying, the error is also varying. And you are finding that as time goes by, the output is actually converging to this final value 1. So I can say that as time goes by, the error value is reducing. Okay, so here the error value is maximum because here the output is 1.4 and input is 1. So how much is the error? 1 minus 1.4, that is 40%. Here suppose let's say it is 0.8. Okay, so how much is the error? 1 minus 0.8, that is 0.2. So here the error is 20%. Here let's say it is 1.1. Let's say it's 1.1. So how much is the error? It is 10%. because output is 1.1. That means here the output is 1.1, so input is 1, so error is 1 minus 1.1, that is 10%. Likewise, whenever, and you are finding that is waveform is always decreasing, so whatever is the amplitude at any instant, previous instant amplitude was greater, so you are finding that at any time the output is actually decreasing, and it is converging to value of 1. Okay, so what is called as 5% settling time. 5% settling time is here, means what, there is a 5% band, there is a 5% error band. 5% error band means lower value will be 0.95 and higher value will be 1.05. Okay, so whenever this waveform is entering this 5% error band, that means here the error is entering 5% error band, 0.95, and you are finding that this waveform is never exceeding this 5% error. So here the value was 0.95, then it is going up. If it had exceeded 1.05 and going out, then I could not have taken this point. Okay, so here the waveform is entering the 5% error band. What is meant by 5% error band? That means the response is entering 0.95 to 1.05 band. Okay, this is called as 5% error band. If I say 2% error band, that means what? This is 0.98 and this is 1.02. So what is meant by 2% error band? So 2% of 1, that is equal to 0.02. So 1 plus minus 0.02, that is 2% error band. 5% error band is 1 plus minus 0.05. So if I am asking you what is the 5% settling time, what is meant by that? 1 plus minus 0.05, that means 0.95 up to 1.05. So whenever the waveform enters this 0.95 to 1.05 band and does not leave that band anymore, that time is called as 5% settling time. That means the output is in between 0.95 to 1.05. उससे ज़्यादा deviation नहीं होगा. It will not come below 0.95. It will not go above 1.05. That time when the waveform enters this 5% error band is called as 5% settling time. What is the error here? Error here is 40%. Now error here is 20%. Error here is 10%. Are this within the 5% error band? Answer is no, because in this case the error is beyond 5%. But here you are finding that, so this is the error, this is 0.95 amplitude and this is 1.05 amplitude. You are finding that here the system response is entering 0.95 to 1.05 range and it is not going out of that band. Okay, so that's why this time is called as 5% error band. That means maximum error can be in between 5%. That means lower side it will be 1 minus 0.05, that is 0.95. Higher side it will be 1 plus 0.05, sorry, 1 plus 0.05, that is 1.05. That means it is not exceeding that band. What is meant by 2% settling time? Here it is 0.98 and here it is 1.02. So 2% settling time is actually towards the right. So here if this is 5% settling time, 2.2% settling time might come here. Okay, so 2% settling time means after this point, so 2% settling time is a time. We have to say that after this point, the amplitude will not be less than 0.98 or will not be above 1.02. So these are the things you write down in your book. So what is meant by 5% settling time? That is after this time, the amplitude of the oscillated waveform or output waveform will not be below 0.95. Below 0.95 हो रहा है मतलब output is exceeding that 5% band. So after this 5% settling time, amplitude of the waveform will not be below 0.95 or it will be neither above 1.05. So at 5% settling time point, the waveform is entering the 5% error zone. What is meant by 2% settling time, which might be here? Okay, so you have to say that 2% settling time means after this point, the waveform is not going to come below 0.98, or after this point, the waveform is not going to exceed 1.02. So it will not cross that 2% error band. So here I have shown 2% error band. That means after within this, the waveform will be confined between 0.98 up to 1.02. So obviously we'll be finding that 5% settling time will be less than 2% settling time. What is the formula? 2% settling time. So first actually we are supposed to see 5% settling time because it comes first. So if the error band is specified as 5%, then the settling time is called as 5% settling time. So here this TS, so we calculate 3 divided by zeta omega n. Okay, what is zeta omega n? It is I think called as time constant of the system. Very important. So zeta into omega n is called as time constant of the system. So 3 by zeta omega n is called as 5% settling time. That means after this time, the waveform is not going to create an error of plus minus more than 5%. What is meant by 2% settling time? The formula is 4 by zeta omega n seconds. Okay, and for 2% settling time is in the more right side. That means width of 2% settling time is more than 5% settling time. This we have to understand. And peak overshoot, how to find out how much is going to be the maximum peak overshoot? This is mp is equal to e raised to, so this thing is e raised to minus pi zeta divided by 1 minus zeta square. So here pi value is 3.14. So smaller value of ts, tp, td, tr, that means smaller value of delay time, rise time, settling time and peak time means that faster transient response or faster system, or system is getting stable faster. Okay, so smaller value of ts, tp, td, tr means faster transient response or faster system. So initially whenever the waveform is showing some undulation, that part is called as steady state transient, and after the settling time whatever response we get is called as steady state response. So transient response for any system should be as small as possible, because we want the waveform, output waveform, to get settled as soon as possible so that we can go for the analysis of the system or next part. So smaller is the value of TP, TS, TD, TR means faster transient response or faster system. This specification occur during transient response. Steady state response starts after TS or after the point A. So if you see this response again, so this is having mainly two part. So from 0 to TS, this part is called as transient, and after this settling time, let it be 2%, let it be 5%, it depends on the designer. So let us say 2% settling time, which is more settled waveform. So this is 0.98 and the waveform is entering the 2% band. So after this starts the steady state, and complete steady state, when it happens at 5 divided by zeta omega n. So if you are substituting 5 divided by zeta omega n, you are finding almost output is reaching the input. So these were the things I wanted to tell you. So what is point A? So at this point the response went inside the 2% error band. That means the waveform will not exceed 1.02, the waveform will not come below 0.98. So it will sustain within the 2% error band, and 2% error is almost equal to 0 error. So at this point the response, went inside the 2% error band and stayed inside it. This is very important thing. So at this point the waveform went inside the 2% error band and stayed inside it. Hence t is equal to 0 to t is equal to ts, that is 2% settling time, is known as 2% settling time. What is 5% settling time? 5% settling time happens before. Okay, so 5% settling time is less, 2% settling time is more, and all these things we can calculate by means of some numerical. So many numericals I have done. I'll go very fast, just check. This is CS by RS. Question is find all the time specifications. And all this numerical starting from page number 9 to 15, I want you to practice today itself. Okay, so एक बार करके रखो, done for lifetime. So 1 by s square plus s plus 1. So in this case the value of k, okay, this is the value of k, that is the system gain, is equal to 1, omega n square is equal to 1. So first thing you are supposed to do is write down what is the generalized equation of CS by RS. So it is omega n square, s square plus 2 zeta omega n s plus omega n square. This omega n square is equal to 1 because you are finding the transfer function, that is 1. So omega n square is equal to 1, and 2 zeta omega n is equal to 1 as well. So 2 zeta omega n is nothing but the coefficient of this s. So if you are doing that, what you are finding is omega n square is equal to 1, and units are very important. So omega n square is equal to 1, omega n is 1 radian per second. 2 zeta omega n is equal to 1, zeta is equal to 0.5. So as soon as you are finding 0.5, you have to give a comment there, that is zeta is in between 0 to 1. That means zeta is a underdamped system. Had you found zeta is 1.5, all these formulas are of no use, because overdamped system does not have any of this time parameters. These time parameters, percentage MP and all, it is appearing only if zeta is less than 1 and greater than 0. So whenever, generally we ask underdamped system only, because we want you to find out all these parameters. So zeta is equal to 1 by 2 zeta n is equal to half 0.5, and as soon as you find zeta is 0.5, you have to tell that system is underdamped. And all these formulas are applicable when it is a underdamped system. So what is omega d? Omega n root under of 1 minus zeta square. So omega n is 1, root under of 1 minus zeta square, zeta is 0.5, so zeta square is 0.25, 0.866 radian per second. Please mention unit, otherwise I'll cut 2 marks Even if you are getting the answer correct, if you are not writing the unit, I'll cut the marks. Theta is equal to tan inverse root under of 1 minus zeta square by zeta. So 0.866 divided by 0.5, it is 60 degree or pi by 3 radian. Here I have written wrong, so pi by 3 radian it should be. So theta is equal to pi by 3 radian, so 1.047. Sorry, this pi by 3 degree. Here pi is 180, and here if you are just doing it in the calculator, so if you are setting the calculator in radian, you will find 1.047. So this top line you can ignore, okay, because this is calculated in degree. Degree is of no use. Or after you find this is 60 degree, you have to convert that thing into radian, that is 1.047 radian. So this top line you can ignore, okay, initially, because you have to calculate everything in radian. So only you should know what is the formula: tan inverse root under 1 minus zeta square by zeta. Then TD, what is delay time? So delay time is when the waveform is reaching to 50% of its final output. So it is 1 plus 0.7 zeta. So zeta we have found 0.5, omega and we know 1. So it is 1.35 seconds. So what you have to check is delay time is 1.35 seconds. So when the waveform reaches to 50%. Then rise time, pi is 3.14 minus theta. Theta is 1.047. Please don't substitute theta as 60 degree. कुछ नहीं आने वाला है. Okay, you will get TR in negative, and that is the end of the numerical. So pi minus theta, theta is in 60 degree, that is 1.047 radian. Omega D is also in radian per second, 0.866 we have calculated. So TR comes to be 2.418. So rise time, delay time was 1.35, rise time will be little greater than that. If you are having rise time less than delay time, means you are on wrong track. Okay, so be careful. So TD सबसे कम width, उससे थोड़ा ज़्यादा rise time, उससे थोड़ा ज़्यादा peak time, उससे थोड़ा ज़्यादा 5% settling time, and सबसे ज़्यादा है 2% settling time. This you have to remember. TD is lowest, TR is little bigger than that, TP is little bigger than that. Then comes 5% settling time, then comes 2% settling time. This is the ascending order. So what is TP? Pi by omega D. So in that case, pi minus theta by omega D is TR, and pi by omega D is TP. That is 3.267. And you will find that all these amplitudes are increasing. Okay, 2% settling time I have found first, but actually I am supposed to find 5% settling time first. That is 3 by zeta into omega n. So zeta is 0.5, omega n is 1. This is 6 seconds. 2% settling time is still rightward. So error has reduced, diminished till. So this is 4 by zeta omega and this is 8 seconds. So you can find out this is T delay 1.35 seconds. This is T rise 2.418 seconds. This is TP, that is peak occurs here. And how much is peak? Percentage MP minus pi zeta divided by root under 1 minus zeta square. Pi is 3.14, zeta is 0.5, and root under of 1 minus zeta square is equal to 0.866. So you are finding it is multiplied by 100 you have to do. So you will get here 0.163 multiplied by 100, that is percentage overshoot is 16.30%. Percentage overshoot is 16.30 means here you are going to get maximum peak as 1.163. That you have to understand. So 1.163 will be the maximum amplitude, and then subtract that from 1. So 1.163 minus 1, that is 0.163 multiplied by 100%, that you are going to get as percentage overshoot as 16.3%. And you are finding that 5% settling time is 6 seconds, 2% settling time is 8 seconds. So this is the best numerical. Page number 9 you can write down. First practice this numerical, and there are many numericals like this given afterwards. All are under damped conditions. So next case we have given 25, 6 as 25. So in this case omega n is equal to root under of 25, that is 5 radian per second, and 2 zeta omega n is equal to 6. So in that case 6 is equal to so 2 zeta omega n is equal to 6. So 2 into omega n and 6 by 2 into omega n. So that is zeta is equal to 0.6. So in that case we have found zeta is equal to 0.6. You have to write this thing, that is zeta is in between 0 to 1. So it is underdamped system. Find omega d. So omega d is 5 minus root under of 1 minus zeta square, that is 5 into 0.8, that is 4 radian per second, and theta. So as soon as you are finding zeta, first job is to find what is omega d and what is theta. Because in the equation of CT, so one thing I did not ask you to write here, I will ask you to write here, write the full equation of CT. Okay, so write the full equation of CT means first you have to find what is omega d, then you have to find what is zeta, and then in the equation, this equation, you have to substitute all the value of omega n, omega d and zeta, and you have to tell me what is the full equation of CT. That is another thing that will also be asked for 2 marks. So these are initial stage, that's what I am not stretching you, but I think I have written it here. So this is how the CT equation look like. So let us see this numerical and stop. So omega d is 4 radian per second, theta is equal to something 0.927 radian. So degree में calculate करो ही मत, calculate everything in radian. Then TD 1 plus zeta into omega and whatever. So this is the formula. So this is zeta 0.6 and this is equal to 0.7. What is 0.7? What is 0.7? Okay, 0.7 is the formula. So 1 plus 0.7 into zeta by omega d, that we have found out here. TR we have found pi minus theta. So theta we have calculated as 0.927 divided by omega d. Likewise, we have found out TP is pi by omega d 0.785. So see that all these things are increasing. 0.284 उससे थोड़ा ज़्यादा, 0.55 उससे थोड़ा ज़्यादा, 0.785, because this is delay time, this is rise time, 100% output, this is peak time whenever we are getting the peak percentage MP, then 5% settling time. Okay, that is that is 1 second, and then 2% settling time, that is 1.33. So I have made a mistake. So 2.5% settling time you calculate first, and then calculate 2% settling time. So first you calculate TD, then TR, then TP, and 5% settling, that is 3 by zeta omega n, and then 2% settling time, and finally percentage MP. So calculating this 6 actually will give you 10 marks. And finally, I have calculated what is 1 minus e raised to minus zeta omega n t divided by 1 minus zeta square sine omega dt plus theta. That is the equation of CT. So this is the equation that you are going to get when you are finding the step response of a second order RLC system. So these are the things that I want to tell you. This is another numerical where I have given you GS, and I have told you that it's a unity feedback. So first you are supposed to find out what is GS divided by 1 plus GS. That means first you are supposed to find out what is the loop gain. So in this case, first you have found out CS by RS, GS by 1 plus GSHS. You are finding it in terms of K. So you are finding K divided by S square plus 10S plus K. So this is in previous numericals, I was giving you this directly with the value of K given. In this case, I have not given you the value of CS by RS. I have given you the GS and HS, and HS is not mentioned. If not mentioned, you can take HS equal to 1. Question is, if this is the value of GS, so here I have mentioned GS as K. Find the gain K so that the system will have damping ratio 0.5. So this is a very important numerical. Page number 11, start with this. You will understand this numerical, so there is nothing difficult. Only you have to find the value of K, so that you are finding the damping as 0.5. So in that case, you are finding first the equation of CS by RS in terms of K. Compare it with omega n square divided by S square 2 zeta omega n s plus omega n square. Then if you are calculating these two, you are getting two formulas. There is omega n is equal to root K and zeta is equal to 10 by 2 omega n. So from there 5 by root K. And there you are supposed to equate this as 5 by root K, that is the zeta is equal to 0.5, because it is asked that I want the system to be having zeta is equal to 0.5. So equating these two, you are finding K is equal to 100. If you are finding that, then substitute in this equation 100 divided by S square plus 10S plus 100. So you are finding omega n is equal to 10, zeta is equal to 0.5. In that case, all the everything you can find out. Again, you are finding that percentage MP is 16.3. So I will post this PDF in your class today, and all these numericals, okay, that you are seeing here, all this numerical you have to solve and practice. So that's all from me now. Maybe with all this, when you understand, when you digest, we will be finding what is called as the MATLAB based CT equation. So MATLAB based response in time domain for a second order RLC system with step input, that we will do on the next day. Or I will do this 1 or 2 numerical maybe tomorrow. Those who don't do it, don't practice it at home. And after that, I will start with the MATLAB. So most probably tomorrow we'll start with MATLAB. Please practice this numerical today itself. Keep practice karo. And if you find any small mistakes and all these things in calculation in my note, please let me know. That's all from my side. Thank you.